Hello and welcome back. In this video we're going to learn how to solve a particular type of differential equations called separable differential equations. Now separable differential equations are of the form dy dx equals g of x over h of y. So we're still focusing on that class of differential equations dy dx equals f of x comma y. But we're saying that if we have a differential equation where the f of x comma y, where the right side of that kind of differential equation, if that can be written in the form g of x over h of x, so in other words a function of x over a function of y, then we would say that that differential equation is separable. It's like you can separate the x and the y variables, the x variables going on the top and the y variables going on the bottom. If you do have a differential equation like that, we can take the following steps to solve the differential equation. We can take the h of y and put it over on the left side, take the dx and put it over on the right side, kind of treating the dx like a differential, and then integrate both sides. So another way you can think about separable differential equations is if you can create something like this where all the y's are on the left side and all the x's are on the right side. So we've separated the differential equations, like two people that are fighting and you separate them, you break them up, then you can integrate both of them. I don't know what that means in terms of people integrating those people that were fighting. I guess you calm them down to complete the analogy. Now these steps take proof. We can't just grab this dx and put it over to the right hand side. That's heresy. So they take proof. It takes proof. And at the end of these notes we're going to prove why we can take these steps. But for now, we're just going to take them for granted and see some examples of how we can use them to solve a separable differential equation. So example 4 says, find the general solution for the following differential equation. dy dx equals 1 plus y. So it looks like we have the right-hand side written as a function of x over a function of y. Now, well, it's not exactly a function of x over a function of y as it's written. We could write this though as 1 over 1 plus 1 over 1 over 1 plus y if we wanted to make sure that the function of y is down on the bottom of a fraction. But don't worry too much about getting it exactly in this form g of x over h of y. Just make sure that you can separate the y variables on the left side of the equation and then on the right side of the equation. Well, we can do that. We can divide both sides by 1 plus y. So we've got 1 over 1 plus y on the left side. We'll put a dy here, and then the dx we're going to multiply over to the right side. Now I'm going to put a little cautionary note here. Whenever you divide by something that has a variable in it, you do have to worry a little bit. When you divide by 1 plus y, what is it you have to worry about? What if y is equal to negative 1? Then you've just divided by 0. So you can only really take this step as long as y is not equal to negative 1. We're going to circle back around to that. What if y is equal to negative 1? What would happen then? But for taking this step, we're assuming that y is not equal to negative 1. We're just covering all the details. Now that the y's are separated from the x's, x's are on the right, y's are on the left, we can integrate both sides. Now on the left side we have ln, absolute value of 1 plus y, and on the right side the integral of 1 with respect to x would be x. We're going to put our plus c here because we're done integrating. We don't want to forget about that. And now our goal is going to be to not just find the general solution, but solve it for y explicitly. That'll be the default, and unless it's like super duper hard to solve for y, if you had a y on the outside of the ln, then it'd be really difficult to solve for y. But usually I'll mention it in the directions, like make sure to solve for y explicitly. And that's usually the default of what you'll want to do. So to solve for y, we need to get at y, and we need to undo that natural log that's keeping y hostage. So we're going to apply the exponential function to both sides, and we get the absolute value of 1 plus y equals e to the x plus c. Okay. Now, one thing is, on the right side, it's gonna be useful to separate the constant out. So what we're gonna do is we're gonna write e to the x plus c as e to the x times e to the c, just using an exponential property to break that up. And we're also going to take a step where we get rid of the absolute value bars. So we're going to write 1 plus y equals plus or minus e to the x, e to the c, I'm going to write e to the x. I'll put the e to the c in the front because we're going to rope it in with the plus or minus. Okay, let's pull it over to here. To solve for y, we have one more step. We'll subtract 1. And now we could leave it like this, but oftentimes you'll see that constants are simplified to other constants. What I mean by that is, here we have a plus or minus e to the c. Now if c is a constant, e to the c is a constant. And then plus or minus e to the c will also be a constant. So it's going to represent some kind of constant. For some value of c and some positive or some negative, this whole thing will just be a constant. So what we're going to do is call k plus or minus e to the c. So that our solution becomes y equals k e to the x minus 1. All right. So this is done all the time in differential equations. If you have something times a constant, or you have like e raised to a constant or something like that, as long as what you get is still a constant, then you can rope it together into another constant. Just call k that new constant. You're just roping all of that together. Sometimes it helps to think, okay, all of this is turning into k. Okay, I wanted to mention a couple of notes here. One is that if you think about all of the possibilities for c can be any number, right? Any real number. If you think about running through all the possibilities for c, you get e to the c is going to be a positive number. Then if you do plus or minus that, you're going to get either a positive number or a negative number. In other words, plus or minus e to the c can never be equal to 0. So I'm going to point that out here. Note a can't be 0 because plus or minus e to the c can't be 0. So the other thing I'm going to mention is when we took this step where we dropped the absolute value bars and we wrote the plus or minus on the other side, I just want to clarify that because sometimes people get confused about that step. Remember, if you have the absolute value of x is equal to 3, then there are two possible solutions to this equation. Either x is positive 3 or x is negative 3. In other words, x is plus or minus 3. So the same principle applies over here. If 1 plus y equals positive e to the x plus c, then you've got a solution. Or if 1 plus y is negative e to the x plus c, you've got a solution. So if you drop the absolute value bars, you'll just put a plus or minus on the other side. The one last thing I want to mention is something we talked about at the beginning of the problem. We said that we could only take this first step if y is not equal to negative 1. Well, what would happen if y is equal to negative 1? Let's mention that down here. So note, if y is equal to negative 1, well, that would be a constant, and the derivative of a constant with respect to x would be 0, so dy dx would be 0. So that would be the left-hand side of your differential equation. And on the right-hand side, the 1 plus y, if y is a constant -1, that's 1 plus -1, which is also 0. So if y is equal to the constant 1, if like y of t, your function is equal to -1, then we do still have a solution to the differential equation. So we also get a solution to the differential equation. Now, what you could do is you could bring your general solution, the k e to the x plus minus 1, and combine it with this other solution, y equals -1, together, because what you could do is just let k be any value. We said that here k was not equal to 0 in this step, but if you let k equal to 0, you get the function y equals -1. So if you allow k to be 0, so that way it includes now any number, then this y equals k e to the x minus 1 would be the general solution where k is all real numbers, or any real number, I should say. It's not all of them at the same time. So there are a bunch of little details to work out with these differential equations, but it is worth it to talk about them. Looking at example 5, we're asked to find the general solution to the following differential equation: y prime equals 2xy plus 2y, where y is positive. So our first job is going to be to separate the variables. We're going to try to get all the y's on the left and all the x's on the right. So we have some function of y times dy equals some function of x times dx. The way we can do that is first, actually I'm going to write the y prime as a dy dx. We can look at the right hand side and think, okay, we have a common factor of y and a common factor of 2 for that matter. So if we factor out the 2y, now at least we've got the 2y and the x plus 1 multiplied together on the right hand side. So now what we could do is divide over whatever y's we have and then multiply the dx over to the right, and then we will have separated the x's and the y's. So we'll do in the next step. 2 over y, or 1 over 2y dy equals x plus 1 dx. We've separated the y's on the left and the x's on the right. Now we can integrate both sides. Now the half is a constant that can hang around. And then we have the integral of 1 over y, which is ln absolute value of y. Then we have x squared over 2 plus x plus c. Now here, y is greater than 0. Y is positive. So we can drop these absolute value bars. So that's kind of nice. We don't have that plus or minus situation that's going to come up, that would come up, or came up in example 4. What we can do is multiply both sides through by 2. I'm going to drop the absolute value bars, multiply through by 2, so we have ln y equals x squared plus 2x plus 2c. Then apply the exponential to both sides to get rid of the logarithm. So we have y equals e all to the power of x squared plus 2x plus 2c. And now, just like in example 4, we're going to break the constant aside. So we'll use the exponent property. Take it up here. To write e to the 2c times e to the x squared plus 2x. So we're breaking off the e to the 2c. And the reason for doing that is because then we can write, instead of e to the 2c, we can write k. Oops. K is just some other letter that represents a constant. Some people, when they're writing this out, they'll just, instead of writing e to the 2c, they'll just write c. which is a little bit sloppy because you're using the same variable c to mean something else in your solution. But some people do it nonetheless. They just say e to the 2c, that's a constant, I'll just call that c. But here we're going to be nice and use a different letter. So we have k equals e to the 2c. So y equals k e to the x squared plus x. Now, one thing we probably should mention is that when you take the 2y and you divide it to the left, remember that we said in the last example, we got to be a little bit careful. But here, we're okay if you can divide by y. The reason for that is that y is greater than 0. So we don't have to worry about y equal to 0 when we're dividing this over. Y can't be equal to 0 because it says y is greater than 0. So that step we didn't have to circle back around to and think, well, what if y were equal to 0? Because it can't be. So that's all for separable equations. Thank you for watching, and see you in the next video.